So we were looking at this metric called node status condition PID pressure. And this indicates whether the node status condition PID pressure is true. P standing for process ID, and we explored the significance of that. The next metric is called node status condition disk pressure. This indicates whether the node status condition out of disk is true. Only you can get that with enhanced observability. Node status condition _unknown. This indicates whether any of the node status conditions are unknown. Only with enhanced observability can you get that metric. Node interface network RX _dropped. So RX usually stands for received. This is the number of packets which were received and subsequently dropped by a network interface on the node. So it's called node interface network. I wish it was called network interface, but it's called interface network RX dropped. Next metric, node interface network TX dropped. The number of packets which were due to be transmitted but were dropped by a network interface on the node. Node disk IO _service _bytes total. This is the total number of bytes transferred by all I/O operations on the node. You can't get that on Windows. You can't get this node disk IO service bytes on Windows. It's only available with enhanced observability. Node disk IO serviced total. This metric is available only with Container Insights with enhanced observability for EKS. It is not available on Windows. It's the total number of I/O operations on the node. The next metric is pod CPU reserved capacity. The CPU capacity, this is reserved per pod in a cluster. And this comes from a formula. It's pod CPU request over node CPU limit. The metric which is pod CPU request is not reported directly as a metric, but it is a field in the performance log events. The next metric is pod CPU utilization. It's the percentage of CPU units being used by pods. This comes from a formula. It's pod CPU usage total over the node CPU limit. And pod CPU usage total is not reported directly as a metric, but is a field in performance log events. The next metric is pod CPU utilization over the pod limit. And it's the percentage of CPU units being used by pods relative to the pod limit. And this comes from a formula. And the formula is pod CPU usage total over the pod CPU limit. And a quick note, pod CPU usage total and pod CPU limit, both of those are not reported directly as metrics, but available as PLEs. The next metric is pod memory reserve capacity. It's the percentage of memory that's reserved for pods. This comes from a formula. It's pod memory request over the node memory limit, And note that pod memory request is not reported directly as a metric, but is a field in PLEs. And the next metric is pod memory utilization. So we've had pod memory reserved capacity and now pod memory utilization. It's the percentage of memory currently being used by the pod or pods. And this is from pod memory working set, that metric, over the node memory limit. Note that pod memory working set is not reported directly as a metric, but is a field in performance log events. The next metric is pod memory utilization over the pod limit. This is the percentage of memory that is being used by pods relative to the pod limit. If any containers in the pod don't have a memory limit defined, then this metric doesn't appear. And this comes from a formula. It's the pod memory working set over the pod memory limit. We have pod network RX bytes, received bytes, the number of bytes per second being received over the network by the pod. And this comes from a formula. It's the sum function of the pod interface network Rx bytes. So this kind of comes from another metric. Pod interface network received bytes, that's not reported directly as a metric. I thought it was pod interface network Rx bytes. What were we looking at then? Pod memory utilization, pod memory reserved capacity, pod CPU utilization over the pod limit, pod CPU utilization, pod CPU reserved capacity. What were we looking at? That was for the node interface network TX dropped. You're right, that mentioned interface network, which is I think what you're thinking of, but this was about dropped. This was the dropped metric, and this one as well as dropped. So yes, it has interface network. You thought that was the one we've dropped in where interface network you thought they were interface network received bytes, but no. Interface network received bytes is not directly reported as a metric, but it is useful if we take the summation of it. And then we have pod network transmitted bytes, and this is the number of bytes per second being transmitted over the network by the pod, and this is a summation. Pod network transmitted bytes. It's a summation of the pod interface network transmitted bytes. Pod CPU request. It's the CPU requests for the pod. This comes from a formula. It's the summation of the container CPU requests. But note that pod CPU request is not reported directly, isn't it? Is not reported directly as a metric, even though it's right here, pod CPU request, but is a field in performance log events. Next metric is pod memory request, the memory requests for the pod. And we're told again in a note that pod memory request is not reported directly as a metric, but is a field in performance log events. Next, the pod CPU limit, and you can see we're repeating all the metrics that we had for the nodes. This is the CPU limit defined for the containers in the pod. If any containers in the pod don't have a CPU limit defined, this metric just doesn't appear. And this comes from the sum function of the container CPU limit. So we add up all the container CPU limits and we get the pod CPU limit. Next metric, pod memory limit. This is the memory limit defined for the containers in the pod. If any containers in the pod don't have a memory limit defined, then this metric doesn't appear. This is just the sum of the container memory limit. And pod status failed. It indicates that all containers in the pods have terminated, and at least one container has terminated with a non-zero status or was terminated by the system. What does that mean? So I'm reading the CloudWatch documentation, specifically container insights. Now one metric is pod underscore status failed. The description puzzles me. It goes like this. Indicates that all containers in the pod have terminated. and at least one container has terminated with a non-zero status, or was terminated by the system. What does it mean when it says non-zero status? In the context of container and even pod termination, a pod is a group of containers in Kubernetes, which applies to metrics like pod status failed. A non-zero status refers to the exit status code of a container that indicates an error or abnormal termination. So this brings us on to exit status codes. When a process, including a container, terminates, it returns an exit status code to the operating system. 0 is conventionally used to indicate that the process completed successfully without any errors. A non-zero status indicates that the process encountered some form of error or did not complete as expected. So non-zero status seems to just mean with an error. If a container terminates with a non-zero status, it means that something went wrong during its execution. This could be due to a crash, a failure to complete a task, an exception in the application running inside the container, or any other problem. In Kubernetes, the pod status failed metric is triggered when all containers within a pod have terminated, and at least one of the containers has terminated with a non-zero exit status code, or was terminated by the system, perhaps due to resource limits or node pressure. Example: a container successfully completes its task, e.g. finishes a script or process without any issues, and exits with a status of 0. The pod would not be marked as failed in this case. Non-zero status: a container tries to perform an operation, e.g. a web server crashes or a script encounters an exception, and it exits with a status of 1 or another non-zero value. This means the container failed, and the pod's status may be marked as failed. Okay, so a non-zero status simply refers to an error or abnormal exit condition for a container. And you can only get pod status failed if you've got enhanced observability. The next metric is pod status ready. This indicates that all containers in the pod are ready, having reached the condition of container ready. And look at the so we have one column for dimensions with any version of container insights. And then the third column is additional dimensions with container insights with enhanced observability for EKS. So the dimensions you can use for pod status ready are cluster name, or you can have a specific cluster and a particular namespace and a pod name, or a particular cluster and a namespace and a service, or a particular cluster and a namespace and a pod name and a full pod name. So we've got pod status ready and then pod status running. This indicates that all containers in the pod are running, all of them. Actually, what is that all about though? That metric seems to indicate a boolean or some value where there's some variable where there are only two values. Either all the pods have failed or they have not. It's either true or false. This seems a strange sort of value for a metric to represent. Don't metrics usually represent variable values like CPU usage, where it can be any percentage value. You're right that most CloudWatch metrics typically represent quantitative values like percentages, or like CPU usage, or counts like request count. However, Kubernetes pod status metrics like pod status failed can indeed act more like boolean indicators or flags. That's the term they use in Kubernetes, flags, for kind of things that can only take two values to signify the health or the state of a pod. Why a boolean-like metric? The pod status failed metric is part of Container Insights in CloudWatch, and it specifically focuses on whether a pod has failed based on its exit status or whether it was terminated by the system. While it may seem binary, it serves a very important purpose in monitoring containerized applications. This type of metric helps answer the question, has the pod failed or not? If pod status failed indicates a failure, a value of 1 or true, because after all, we're not told the kind of the units. Usually there's a unit thing in the docs. If pod status failed indicates failure, you know something went wrong, and you can investigate further. Though it sounds binary, metrics like pod status failed can be used to count the number of failed pods over time. For instance, if you have 10 pods running and 3 fail, the metric could reflect the number of failed pods, e.g. 3. Okay, that's fine. We have pod status running. It indicates that all containers in the pod are running. We have pod status scheduled. It indicates that the pod has been scheduled to a node. We have pod status unknown. Indicates the status of the pod can't be obtained. We have pod status pending. It indicates that the pod has been accepted by the cluster, but one or more of the containers has not become ready yet. We have pod status succeeded. This indicates that all containers in the pod have successfully terminated, and will not be restarted. We have pod number of containers. It reports the number of containers defined in the pod specification. We have pod number of running containers, reports the number of containers in the pod which are currently in the running state. We have pod container status terminated, reports the number of containers in the pod which are in the terminated state. That's pod container status terminated. We have pod container status running, reports the number of containers in the pod which are in the running state. Of course, before it was about the pod itself. Now we're saying what's the status of the containers. So we have pod container status running, pod container status waiting, container being the operative word, pod container status waiting, reason, crash loop, back off. This reports the number of containers in the pods which are pending because of a crash loop back off, error, where a container repeatedly fails to start. That is my favourite metric. Pod container status waiting, reason, crash loop, back off. We have pod container status waiting reason, create container config error. This metric reports the number of containers in the pod which are pending with the reason, create container config error. This is because of an error while creating the container configuration. Next metric, pod container status, waiting reason, create container error. This reports the number of containers in the pod which are pending with the reason, create container error, because of an error while creating the container. We have pod container status, waiting reason, image pulled error. This reports the number of containers in the pod which are pending because of error image pull back off, or invalid image name. These situations are because of an error while pulling the container image. Pod container status waiting reason, OOM killer. This reports the number of containers in the pod which are in the terminated state because of running out of memory. OOM, out of memory. The next metric is called pod container status waiting reason start error. This reports the number of containers in the pod which are pending, with the reason being start error, because of an error while starting the container. Next is pod interface network RX dropped. The number of packets which were received and subsequently dropped by a network interface for the pod. Pod interface network transmitted dropped, TX dropped. The number of packets which were due to be transmitted but were dropped for the pod. Container CPU utilization, the percentage of CPU units being used by the container. This comes from a formula, it's container CPU usage total over the node CPU limit. Container CPU utilization over container limit. The percentage of CPU units being used by the container relative to the container limit. If the container doesn't have a CPU limit defined, then this metric just doesn't appear. And this comes from a formula, the container CPU utilization over the container limit. Can you think what it would be? It's over the limit. How many containers have the CPU utilization over the container limit? Well, we need the container limit to be in there somewhere, so we divide by the container CPU limit, and the thing on top is the container CPU usage total. The next metric is container memory utilization. This is the percentage of memory units being used by the container. This comes from a formula. On top we have the container memory working set, and we divide it by the node memory limit, so the limit for a particular node. And next we have container memory utilization is over the container limit. So the percentage of memory units being used by the container relative to the container limit. If the container doesn't have a memory limit defined, then this metric doesn't appear. And this comes from a formula. We have the container memory working set over the container memory limit. The next metric is container memory failures total. The number of memory allocation failures experienced by the container. Next is the pod number of container restarts. This is the total number of container restarts in a pod. Next is service number of running pods. This is what, the number of services? No, the number of pods running the service or services in the cluster. So service number of running pods. How many pods are responsible for this service? Next is replicas underscore desired. This is the number of pods desired for a workload as defined in the workload specification. So it's called replicas desired, but it's actually, it could be called pods desired. The next metric, oh my, is called replicas ready. This is the number of, again, it's pods. Replica means pods. The number of pods for a workload that have reached the ready status. So replicas underscore ready. And this metric is available only with container insights with that enhanced observability for EKS. Next, status replicas available. The number of pods for a workload which are available. A pod is available when it has been ready for the min ready seconds defined in the workload specification. Status replicas unavailable. The number of pods for a workload which are unavailable. A pod is available again when it has been ready for the min ready seconds defined in the workload specification. Pods are unavailable if they have not met this criterion. API server underscore storage underscore objects. API server storage objects. The number of objects stored in etcd etcd at the time of the last check. We have API server request total. The total number of API requests to the Kubernetes API server. We have API server request duration seconds. This is the response latency for API requests to the Kubernetes API server. So it's API server request duration in seconds. It's really a measure of latency. It doesn't have latency in the name, but it is. API server admission controller, admission duration seconds. This is the admission controller latency in seconds. An admission controller is code which intercepts requests to the Kubernetes API server. REST client request duration seconds_seconds. This is the response latency experienced by clients calling the Kubernetes API server. This metric is experimental and may change in future releases of Kubernetes. REST client requests total. This is the total number of API requests to the Kubernetes API server made by clients. This metric is experimental and may change in future releases of Kubernetes. etcd request duration _seconds. This is the response latency of API calls to etcd. This metric is experimental and may change in future releases of Kubernetes. Next is API server _storage and then size _size_bytes. This is the size of the storage database file physically allocated in bytes. This metric is experimental. Next is API server _long-running requests. This is the number of active, what are called long-running requests to the Kubernetes API server. Next, API server _current in-flight requests. This is the number of requests that are being processed by the Kubernetes API server. They're in flight, they're currently being processed. Let's stop here, and I just want to help us to gain a bit of understanding about because you can learn that there are certain metrics, but then there's a second task, which is having that knowledge and experience to read. Well, what does that mean? Read the metrics. What might it mean if the particular metric called API server _long-running requests is particularly high? Please provide some context and background here. What is a long-running request? And what conclusions can I draw? What conclusions can I draw from the fact that there are many long-running requests? The metric API server long-running requests refers to the number of long-running requests currently being handled by By the Kubernetes API server, a particular part of the architecture. In Kubernetes, the API server is a central component that handles all incoming requests to manage the cluster. These requests include actions like creating or deleting pods, just updating resources, and retrieving information about the cluster state. So a long-running request, well, that's a request to the API server that remains open and active for an extended period of time. Some examples of long-running requests include watching a resource. Clients, such as kube control, controllers, or even a custom application, may watch for changes to Kubernetes resources. Changes to a pod, a service. And this involves opening a connection to the API server that stays open until the client disconnects or the server closes the connection, of course. Another example is post forwarding or exec. When users or services use kube control to port forward traffic from a Kubernetes service or to exec into a pod, these actions create long-running requests to the API server. When users use or services use kube control to port forward traffic from a Kubernetes service, I don't know what that means. To port forward traffic from a Kubernetes service. So you send it to one port and it actually goes to another port. I don't know what it means to exec into a pod. But also log streaming. Streaming logs from a container also results in a long-running request. These types of requests are not immediately closed after retrieving data or performing an action, but instead stay open as they continue to stream data or wait for an event to occur, e.g. a resource change in the case of a watch. So what does a high number of long-running requests indicate? It could mean, if it's a high number of watch requests, that many components, watching a resource, that many components in your system, such as controllers, operators, or even custom applications, are actively watching for changes in the cluster. No, it does mean that, doesn't it? Because that's just a restating of what it is. It's like saying a chicken means a chicken. Sorry. This can happen naturally as your system scales, with more clients watching resources like pod services or custom resources. If many users or services are streaming logs, or setting up port forwarding tunnels, this increases the number of long-running requests. While long-running requests themselves are not inherently bad, a high number of them can put strain on the Kubernetes API server. The API server needs to manage and track each open connection, and that can consume memory. It can consume CPU and networking resources. If the number of long-running requests grows too large, it could impact the API server's ability to process other requests in a timely manner. API server saturation. In extreme cases, the API server may become overloaded by trying to maintain too many active connections, leading to delayed or dropped responses for other requests. If clients or controllers are misconfigured, they might open many unnecessary long-running requests. This can happen if controllers or apps are written to aggressively watch too many resources. And that could indicate inefficiencies in the way they are managing connections. If watch requests are broad in scope, e.g. watching for changes across all namespaces instead of a single one, they can unnecessarily increase the load on the API server. So what conclusions can you draw from high long-running requests? So here are some actions you might consider. 1. Check for increased system activity. Investigate whether your cluster is handling more traffic than usual. For example, are there many new workloads being created? Are there more users or applications watching resources or streaming logs? In a growing or scaling cluster, it's normal for the number of long-running requests to increase, especially if many controllers or custom operators are watching resources. 2. You want to monitor API server performance. If the number of long-running requests is high, monitor the performance metrics of the API server itself, such as CPU, memory, and request latencies. So we do have API server _request duration seconds. If the API server is under strain, you may see increased latencies, increased resource usage. You might also monitor failed or rejected API requests. So use API server underscore request underscore rejected total. Check that to see if the API server is unable to handle incoming requests due to load. So 2, you would monitor the API server. 3, investigate the clients, the controllers, the things putting the demands on the API server. You would check for any misconfigured clients or controllers that might be creating unnecessary watch requests or keeping open long-running requests when they're not needed. Review custom applications or operators in your cluster that are opening watch requests to ensure they are efficient and scoped properly. 4. You would consider load balancing or horizontal scaling. If your cluster is experiencing high traffic, consider scaling your API server horizontally by adding more instances. This can help distribute the load of long-running requests and ensure the API server is responsive to all incoming requests. And the 5th thing you might do is tune your watch requests. If you have control over the watch requests, for example from the ones from a custom application, then you might consider narrowing the scope of watches to reduce load on the API server. For example, watch only specific resources or specific namespaces instead of everything in the cluster. Key takeaways. Long-running requests include actions like watching resources, log streaming, or port forwarding, which keeps a connection open with the API server. A high value for API server underscore long-running requests means many open requests are being handled, and that can signal increased system activity, but may also place strain on the API server. You should monitor both system activity and the API server performance when this metric is high to ensure the system remains healthy and responsive. So let's just have one quick follow-up question. What is port forwarding and why does it result in a long-running request? Port forwarding is a technique used to redirect network traffic from one port on a host or server to another port, often on a different machine. In Kubernetes, port forwarding is typically used to allow users to access applications or services running inside a pod on a Kubernetes cluster from their local machine. And this is useful. So the idea is they go to, but why do we need port forwarding for that? Surely you just go to the port, which is the port of the Kubernetes cluster. This is useful when you want to test or interact with an application running inside a Kubernetes pod without exposing the service externally. So, how port forwarding works in Kubernetes? We have a local to pod connection. You initiate port forwarding using a tool like kubectl to connect a port on your local machine to a port on a pod inside the Kubernetes cluster. So you go kubectl and then you type port forward pod/mypod 8080 .80. So 8080 on your local machine will be forwarded to port 80 on the MyPod pod. After this, you can access the application running inside the pod via http://localhost 8080. The Kubernetes API server, our old friend, handles the proxying of network traffic. When you use the kubecontrol port forward command, kubecontrol communicates with the API server, which then forwards the traffic to the specified pod and port within the cluster. So why does port forwarding result in a long-running request? A long-running request is a request that stays open for an extended period of time rather than completing immediately. Port forwarding results in a long-running request because we have a persistent connection. When you set up port forwarding, the connection between your local machine and the pod in the Kubernetes cluster remains open. It's just a fact that it remains open as long as you continue to forward traffic. I'm saying it's a fact because it is contingent. We can conceive of it not being the case. It could be that every time you send it, it just quickly opens it and then shuts it again. And it opens it and shuts it. Why not? So it's just a fact that it just does seem to keep it open, it seems. The Kubernetes API server has to maintain the connection between your local machine and the pod. We also have a point to make about continuous data stream. Since port forwarding allows for a continuous stream of data, such as HTTP requests or responses, SSH sessions, etc., between your local machine and the pod, the connection stays alive for the duration of the port forwarding session. This is why it's considered long-running. No, that's just what long-running means. API server handling. The Kubernetes API server is responsible for proxying traffic from your machine to the pod, which requires it to maintain an open request and connection for the entire duration of the port forwarding operation. Why does it matter? The API server load. Every port forwarding session, because that's what it is, a session, and that should have connotations of something that's long-lasting for you if you work in web or IT. Every port forwarding session results in a long-running request to the API server, which it has to track, which it has to manage. If many users or services are using port forwarding, this could increase the load on the API server, as it needs to handle multiple open connections at once. Monitoring. A metric like API server _long_running_requests helps you monitor how many such open connections the API server is handling. If this metric is high, it might indicate that many long-running operations are occurring in your cluster, which could potentially affect the performance of the API server. What are some common use cases for port forwarding? Debugging and testing. You might want to debug or test an application running in a pod, but the pod isn't exposed to the outside world via a service. Port forwarding allows you to connect to the pod without needing to expose the service publicly. Accessing internal services. Some services may be internal to the cluster and not meant to be externally exposed. Port forwarding lets you temporarily access these services from your local machine for troubleshooting or testing purposes. So I think that's some good background on that metric. So we have this metric called API server long-running requests. We have a metric which is API server current in-flight requests. We have a metric which is API server admission webhook admission duration seconds. Admission webhook latency in seconds. Admission webhooks are HTTP callbacks that receive admission requests and then do something with them. we don't understand that. So what about this metric? API server, admission webhook, admission webhook, admission duration, seconds. Okay. The description reads, admission webhook latency in seconds. Admission webhooks are HTTP callbacks that receive admission requests and do something with them. Can you provide some background here? What is an admission webhook? What is an HTTP callback? Admission webhooks are a critical part of how the Kubernetes admission control process. And the admission control process governs what happens to requests sent to the Kubernetes API server. They allow you to customize and control the behavior of your Kubernetes cluster by performing actions on resources before they are even persisted in etcd, which is the Kubernetes backing store for all cluster data. So, HTTP callback. When a request is made to the Kubernetes API server, it can be processed by an admission controller. If configured, the server will send a request to the admission webhook, which acts as an HTTP callback. Okay. The webhook receives the admission request and can inspect, modify, or reject the request based on certain conditions. The request includes details about the resource being created or modified, such as its kind, its namespace, and any specifications. Decision making. The webhook can accept the request, allowing it to proceed, reject it, stopping it from being processed, or mutate the request, modifying the resource's specifications before it is persisted. And then a response is made. The admission webhook responds to the API server with the admission decision. The API server then continues processing the request based on the response received from the webhook. What is an HTTP callback? An HTTP callback is a mechanism where an HTTP request is sent to a specified URL when a particular event occurs. In the context of admission webhooks, the Kubernetes API server makes an HTTP request to the URL of the webhook, and it does that whenever an admission control event is triggered, so someone creates or updates a resource. It makes a request to the webhook. The webhook can then perform any necessary logic, like validating the request or modifying its content, and send a response back to the API server. So presumably that's why it's called a call back. The webhook is calling the API server back. So it received a call, now it's giving a call back once it's performed the necessary logic. But why is it called a call? Let's just let me just validate that. verify that. Why is it called a callback? Who is calling back who? In what sense is it back? Call and response. So in general programming terminology, a callback refers to a function or a method. A method is just a function for a particular object. A callback refers to a function or method that's passed as an argument to another function and is expected to be called back at some point during the execution of that function, the bigger function. It's a way for a lower level function to execute code defined at a higher level once the specific condition is met. In the context of webhooks, the call refers to the action initiated by an event, like an API request. The back part comes from the perspective of the entity that set up the webhook. Actually, right, so we were wrong. When the event occurs, the system, the Kubernetes API server, sends an HTTP request, that's the call, to the specified URL, and that's the webhook endpoint, to notify the system that something has happened. So who is calling back who? In the case of Kubernetes admission webhooks, the Kubernetes API server, that's what initiates the call when an admission request occurs. The webhook is called back to provide a response. So you can think of the webhook as a service listening for incoming requests. The term callback implies that the webhook will respond back to the API server after processing the admission request. Okay, so we kind of were right, actually. And I think the way it is a kind of the same sense of this programming sense, a function in a function, because the bigger function is the Kubernetes API server, the smaller one within it is the webhook. So why back? Well, the back in callback signifies that the response is sent back to the originator of the request, in this case the Kubernetes API server. So we have the initial call, the Kubernetes API server sends a request to the webhook endpoint. Then we have processing, the webhook processes the request, it validates it, it mutates it. We then have a response back. The webhook sends a response back to the API server indicating what should be done with the original request. Okay. What is a webhook? Hook. It's a user-defined HTTP callback that allows one system to send real-time data to another system when a specific event occurs. Webhooks are widely used for integrating applications and services, enabling them to communicate with each other without the need for constant polling. So when you hear that term webhook, you should just be thinking, I think it's just the fact that they easily integrate. I mean, if you can hook something on, it's easy. You just hook it on. I think that's would be a helpful way of thinking. Do we have to knit them together or glue them together? No, you just hook it on. We don't have to constant poll. We don't have to put one, I don't know, hard code, I don't know. But it's just event driven. Right, when you're ready, it'll be there. So webhooks are triggered by events. The notification is, if it's usually an HTTP request, the notification is typically sent as an HTTP post request, and it's real time usually. Because webhooks push data to the receiver when an event occurs, they actually enable real-time communication between systems. And users can usually configure webhooks by specifying the URL of the receiver and the events that should trigger notifications. Okay. So, why is this metric important? API server admission webhook, the admission duration seconds. If this admission webhook is taking a long time to respond, it will slow down the handling of API requests, leading to increased latency for users and applications interacting with the Kubernetes API. Why is this metric important? It's to do with performance monitoring. Monitoring the latency of admission webhooks helps ensure that they are responsive and do not introduce significant delays in the processing of API requests. High latencies can indicate issues with the webhook implementation or network problems. Debugging. If there are performance issues with a cluster, then examining this metric can help just identify if admission webhook latency is contributing to slow response times. Long response times from admission webhooks can affect the overall efficiency of resource management within the cluster, especially during high load scenarios where many resources are being created or updated simultaneously. Okay. The next metric is API server admission step admission duration in seconds. This is the admission sub-step latency in seconds. Well, this seems the best time of all times to investigate that. Dangerous thought. There's another metric for EKS called API server, all one word, admission step admission duration seconds. It is the admission sub-step latency in seconds. Can you explain what this is and how it differs from the previous metric we discussed? Well, this one with step admission, or admission step in it, measures the latency of specific sub-steps involved in the understanding this metric requires a bit of context about how admission control works in Kubernetes. So, admission control overview. When a request is made to the Kubernetes API server, it goes through an admission control process. This process consists of various steps, including initial validation of the request, processing by admission webhooks, and then final decision making, accept, modify, reject. Steps in admission control. The admission control process can be broken down into several sub-steps, each representing a specific action taken during the admission process. These might include validating the request against Kubernetes policies, mutating the request via admission webhooks, and performing other checks like quota enforcement or resource limits. So, this metric tracks the latency associated with each of these admission substeps. Essentially, it measures how long each individual step takes to process a request during the admission control phase. How it differs from the previous metric. So we had another metric which is API server admission webhook admission duration seconds. So there's no step. This is admission webhook, not admission step. Well, it differs in terms of granularity. Webhook admission, that metric, this measures the total latency of the entire admission webhook processing. This encompasses the time it takes for the API server to send a request to the webhook, wait for that response, and process that response. But admission step focuses on the latency of the individual sub-steps in the admission control process. So we're getting a more granular view of where time is being spent during the admission process. And in scope, the webhook duration metric is specifically concerned, it seems to be, with the performance of admission webhooks. I think that's the word I should emphasize. Which are external systems that the API server interacts with. Yeah, but if it's webhooks, it's almost as if it's saying it's only concerned with a specific part of it. But then up here it said that it measured the total latency of the entire admission webhook processing. So does it deal with the total process or just with the webhooks part? The step duration metric can include latencies from various parts of the admission control process, not just the webhooks. Perhaps this is, I don't think ChatGPT really knows, but this may include internal checks, they're not webhooks, the validations, they're not webhooks, and any other logic defined in the admission control pipeline. Yeah. And so, in terms of importance of the metric, we get a slightly unsatisfying answer. We're just told it seems to be just, you can rule it out if you're having problems. You can rule out a problem with the admission process. Perhaps using this metric, you can determine which specific admission step is contributing to the delay. Okay. Next metric, API server requested deprecated APIs. So this is the number of requests to deprecated APIs on the Kubernetes API server. And we're going to investigate this next time. I must say, I try not to look ahead when I'm reading a big document, because it's just a symptom of just being unhappy about where you are, but I do wonder how much more of this table there is. So what we're going to read next time is investigate next time is the metric API server requested deprecated APIs. So we have page 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58. So we're on the 58th page of this table now. I know some pages don't have much on, but still. And how many pages in total? 58, 59, 60, 61. So we're near the end now, but that's 61 pages of the user guide for elastic Kubernetes service metrics. But this is what it's about. This is where it's taken all this time to get to this stuff. This is the real meat of it, So many discussions of CloudWatch they don't actually mention any of these specific metrics. It's always just vagueness. Oh, it's a monitoring service. Okay, until next time.